Hello everyone. Welcome to PhysicsLoops. Today we're going to solve a puzzle that connects the motion of the Earth and a simple wheel. You'll find out when the planet accelerates, during the day or at night, and which part of a wheel is almost stationary while everything else rushes by. Seems simple? Only at first glance. Let's dive in. Imagine a modern viral post on a popular X channel. The headline screams, "Want to travel the universe for free without leaving your couch? Send 0.001 BTC and get the secret." Thousands of people took the bait. In response, each received just one message. Just lie still. Earth will do it for you. At our latitude, you fly 40,000 kilometers per day. Open the curtains and enjoy the view. The channel author was banned for fraud, but before the block, he managed to quote the classic. And yet it moves! And you know what? In a sense, he was right. We aren't just sitting in offices and apartments. Each of us is a passenger on a cosmic express, rushing through the void at a speed of 30 kilometers per second. But there's a secret hidden here that textbooks stay silent about. Think about it. When is our speed maximal? Day or night? At first glance, the question sounds absurd. After all, Earth spins constantly. But we're not talking about the planet as a whole, but about you personally. Right now, you are participating in two races simultaneously. Earth rushes around the sun and rotates around its axis. These two vectors add up, but the result depends on where you are, on the illuminated side or in the shadow. Look at this invisible mechanics. At midnight, Earth's rotation coincides with the direction of its orbital flight. Speeds add up. You rush through space faster. At noon, it's the opposite. Earth's rotation is directed against its motion around the sun. Speeds subtract. You slow down. Here's the paradox. At night we are faster than during the day. For equator residents, this difference is huge, a whole kilometer per second. For those of us living in mid-latitudes, for example, in Boston, the difference is smaller, but still palpable for physics. At midnight you fly through space half a kilometer per second faster than at noon. So when you go to sleep, remember, you aren't just resting. You are accelerating to maximum speed in orbit. We are all space travelers, even when simply dreaming. Want to run a simple experiment that will hack your perception of reality? Right now. Grab a bicycle or find a car. Stick a bright sticker on the tire. Now ask a friend to ride past you slowly. You'll notice something strange. When the sticker is at the bottom, you clearly see the color and shape. But as soon as it reaches the top, it turns into a blurry spot. It disappears faster than an eye blink. The same happens with the spokes. In the lower part of the wheel, you can count them. In the upper part, they merge into a solid disc. It creates the illusion that the top part of the wheel is simply running faster than the bottom. But this is not an illusion. This is pure physics. The top part of the wheel really does move faster. Sounds crazy? After all, the wheel is solid, spinning around one axis. How can one part overtake another? The answer lies in the same mechanics as our Earth story. Every point on the wheel participates in two races simultaneously. First, rotation around the axis. Second, moving forward together with the bicycle. At the top point, these speeds add up. Rotation pushes forward, and the bicycle pulls forward too. Acceleration sums up. At the bottom point, a conflict occurs. Rotation turns the wheel backward, relative to the ground, while the bicycle pulls forward. Speeds subtract. As a result, for an observer on the roadside, the top of the wheel rushes twice as fast as the axle, and the bottom point is completely stationary. At the moment it touches the asphalt, its speed is zero. That's exactly why the sticker at the bottom is so clear. It freezes for a moment. Don't believe it? Check for yourself. Here's a challenge for the weekend. Stick a pole in the ground or place a cone next to the wheel of a stationary bicycle. Mark a point on the tire at the very top and very bottom, exactly opposite the pole. Roll the bicycle forward just 20 centimeters. Look at the marks. The top one will fly far forward. The bottom one will barely crawl away from the pole. Math doesn't lie. So, when you ride a bicycle, remember? You are controlling a machine where the top overtakes the bottom, and the contact point stops every time, so you don't slip. Physics around us is more complex and interesting than it seems at first glance. So, we figured out. The top of the wheel rushes forward, and the bottom slows down. But who is the absolute champion of slowness? The answer may seem incredible. The slowest point is the one touching the ground. At the moment of contact with the asphalt or rail, it is not just slow. It is absolutely motionless. It freezes. This only works for a rolling wheel. If the wheel spins in place, like a flywheel, all points are equal. But once it starts rolling, the magic of speed addition begins. And now, a bonus task. Imagine a high-speed train rushing from Washington to Chicago. Is there a point on this train that is currently moving backward toward Washington, while the whole train flies forward? You'd say, that's nonsense. But physics says, yes. At every moment in time, on every train wheel, there are points that move in the opposite direction. Where are they hidden? The secret is in the wheel design. You've probably noticed that train wheels have a protruding edge on the inside, the flange. It's needed so the train doesn't derail. And this protruding part behaves paradoxically. The lower points of the flange are further from the wheel center than the rail contact point. Because of this, their backward rotation speed becomes greater than the train's forward speed. As a result, relative to the ground, they slide backward. Don't believe it? Check it in 1 minute. You don't need a train. Take a regular coin and a matchstick. 1. Glue the matchstick with wax or clay to the edge of the coin so it sticks out like a ray. 2. Place the coin on a ruler or the edge of a table. 3. Start rolling the coin forward slowly. Watch the tip of the matchstick. While the coin rolls forward, the protruding tip of the matchstick in the lower position will roll backward. The longer the matchstick, the more noticeable this effect. The train works exactly the same way. Part of its wheel really does travel into the past, even if only for fractions of a second. So, when you ride in a comfortable carriage, remember, somewhere down below, under the rumble of wheels, there are points that stubbornly move backward, contrary to logic and the direction of the train. Physics is full of surprises, even on familiar rails. We've only opened one door. What lies behind the next? Stay on the channel to find out first. Leave your mark with a like and a word. This is fuel for our future research. Physics doesn't forgive boredom. See you again on Physics Loops.